Okay, let's talk a little bit about electrolysis. Now, electrolysis reactions are non-spontaneous reactions. That is, they don't just occur if you were to just a mixture of reactants, but we can make them occur by application of an external current. So, while your galvanic or voltaic cells, we use the fact that the reaction was spontaneous to produce an external electrical current that we could potentially then use to perform some sort of electrical work. In electrolysis, the emphasis is on the chemical reaction and that we're using electricity of a certain voltage and a certain amperage to cause selected chemical reactions to occur. For example, electroplating is a good example of where that would be useful. So we supply the electric current and force it to flow in the opposite way as what would be the normal flow and cause the chemical reaction to occur. So reduction still occurs at the cathode and oxidation still occurs at the anode, but the electron flow is forced to flow from anode to cathode. And so the signs are reversed. In electrolytic cells, the anode is positive and the cathode is negative, where the reverse is true of a galvanic cell. So just to review that, we have a little question down here, which just asks for that. So let's look at this particular question as a review. We got the galvanic cell on the left, the electrolytic cell on the right, where the cathode is still going to be reduction. The anode for the galvanic cell, as we said, is oxidation. And then we said the anode was negative and the cathode was positive. Now, what we said for the electrolytic cell was that the reduction oxidation part does not change. The cathode is still going to be reduction, where the anode is still oxidation. But the difference is the signs on the electrodes are reversed. And you want to keep that in mind going forward. So moving on, here are some examples of electrolysis. A lot of times it is used to produce metals. We can use that current to produce a metal from its oxidized form, say from an ore sample, as in the sodium on the right. In the reaction left, we have molten sodium chloride where the ions are there. So this is a very high temperature. We're getting a reduction of the sodium at one electrode. You can see it pooling around the electrode. And we're getting chlorine gas at the other electrode, which could then be collected as well. But we have to supply that current from a battery or some source of electricity. To do a lab with an electrolysis, well, we're not going to be doing this particular reaction. It'll be similar in design. On a more industrial scale, you could see a setup like what's on the right. You're producing the metal, you're sucking it over to a container where the gas is being often collected. More practically speaking, we can see that the cathode reaction is the reduction of the sodium. The anode reaction is the reduction, or excuse me, the oxidation of the chlorine. Industrially, you can produce metals like aluminum that way quite easily. If you got active electrodes, that means the electrodes are actually taking part of the electrolysis versus an inert electrode like in the previous example, which were made of graphite or it could be platinum. So if I just had our nickel cell and it's all in the same cell, then the nickel anode would lose mass producing nickel 2+ ion, which would then plate out onto the nickel cathode as a for instance, but it doesn't have to be all the same thing. That's just more of an. So if we consider the nickel electrode and another metallic electrode placed in that nickel solution, we get nickel being the oxidation and the reduction. Again, it doesn't have to be the same metal plating both ways. This is just an example. With the nickel plates out on the electrode and electroplating, like galvanizing, which we mentioned in a previous video, is a good example of that. You plate one metal out onto another and protect the structural metal, say iron, with a protective layer of zinc. So if we want to look at some of these electrolysis reactions, we have to apply Faraday's law. Faraday's law states that the amount of substance undergoing a chemical reaction at each electrode is directly proportional to the amount of electricity that passes through the cell, and consequently, whatever the oxidation state is. A Faraday is the amount of electricity that reduces one equivalent of a substance at the cathode and oxidizes one equivalent substance at the anode, or it's a mole of electrons. So 1 Faraday of electricity is Avogadro's number of electrons, or 1 mole. Now, a coulomb is the amount of charge that passes a given point when a current of 1 amp flows for 1 second. So a coulomb is an amp per second. And therefore, the number of electrons flowing past the location, an amp would then be a coulomb per second. Since the charge on a single electron is 1.6 times 10 to the negative 19th coulombs, we can say 1 Faraday is Avogadro's number of electrons, or 96,487 coulombs. Sometimes they'll round that off to 96,500. So 1 Faraday electrons represents that 96,487 coulombs, and that will reduce one equivalent or 1 mole of a substance, or that'll be the amount of electrons produced by the oxidation and the passage of 1 mole of electrons through the electrolytic cell. And so oxidizing or reducing one equivalent is equal to a mole of electrons lost or gained. Here's a table showing that one equivalent. So 1 equivalent of electrons, or 1 Faraday of electricity, reduces 1 mole of silver, or 107.8 grams. You need 2 moles, or 2 Faradays of electricity, to get 1 mole of hydrogen gas, because it's a 2 electron reduction. So 1 Faraday would only produce half a mole, or 1.08 grams of hydrogen gas. Copper is a 2 equivalent reduction, so you'd only get half a mole of copper, or 31.773. Gold is a 3 equivalent reduction, so you'd only get a third of a mole from 1 Faraday of electricity, or 65.656 grams. Chlorine is a 2 equivalent reduction, or oxidation if you prefer. Those are the blue ones are oxidations. And you can see you produce half a mole of chlorine, or 35.453, or 11.2 liters if you're at STP, since it's a gas. Water goes to oxygen gas plus 4H plus 4 electrons, so for a 4 equivalent oxidation at O2, so 1/4 of a mole, or 8 grams, or 5.60 liters at STP. So if we look at that 1 Faraday of electricity going through a metal salt, which ones would be the correct amounts? So potassium is a 1 equivalent reduction. And all of these are for metals, so they're reductions. And potassium has a molar mass of 39.1 grams. So guess what? Hey, that one works. 1 Faraday of electricity will produce 39.1 grams. Now, it's a little bit more complicated looking at some of the others. 27.9 grams of iron from the iron chromate. That means iron would be in the 2+ oxidation state, And so we're looking 55.85 for the molar mass of iron. And I would produce half a mole since that's a 2 equivalent oxidation, which is 27.9. So that one works. We want to produce 10 from tin chloride. And so that's a 2 equivalent reduction. So 118.69 divided by 2 is not going to work because the molar mass of tin is 118.69. That's already the molar mass, and I need half that amount. If we got Al2O3, aluminum's in the 3 plus oxidation state, so 26.98 divided by 3 is 8.99, and I've got 13.5. So that's not going to work because that's divided by 2, not divided by 3. And so that one won't work either. Let's calculate the mass of a palladium. So here's a calculation. So we're going to work through this. We got mass of palladium produced by the reduction of palladium to plus ions. And so that's a 2 equivalent reduction to palladium metal. We got 3.20 amps of current for about 30 minutes. So let's work on that. We'll need the molar mass of palladium as well. So if we go to the paper here, and we're going to need that molar mass, PD, off of the periodic chart. Right there, right? 106.42. So we're going to write that down as well. 106.42 grams per mole. So that's the information from the problem and from the periodic chart. So first thing we need to do is think, remember an amp, that's 3.20 coulombs per second. And so I can't use minutes. I'm going to have to convert that really quick. 1 minute is 60 seconds. And so you're going to have to run that through your calculator, which you may be able to do in your head, but that's going to be 1800 seconds. Now I'm ready to start. Let's start with that 1800 seconds. We'll consider that 3 sig figs since I started with 3 sig figs here. So we'll treat that 0 as significant. And then we're going to multiply that by 30 or 3.20 coulombs per second. Seconds are going to cancel, and then we get the total amount of coulombs applied. Now I need to get this into moles so I can do something with the reaction. That's where that Faraday's constant is going to come in. So we're going to do 96,500 coulombs per 1 mole of electrons. Now that gets me working, and we know how many moles of electrons were actually dispensed. Now that I've got that, now I can use the reaction. There's a 2 equivalent reduction, so it's 2 moles of electrons per 1 mole of palladium. And now we can work it more like a stoichiometry. Per 1 mole of palladium is 106.42 grams of palladium. So then moles of electrons cancel, moles of palladium cancel, we got grams. Now we can calculate everything out. And to 3 sig figs, we're going to say 3.18 grams of palladium. And that would be my answer. All right, let's look at one more example. And this involves a gas, so it's a little different. And this is an oxidation instead of a reduction. We're going to calculate the volume of oxygen measured at STP produced by the oxidation of water if 3.2 amps of current have passed through the water for 30 minutes. So we're using the same amperage and the same time from before, but different reaction. Notice this is a 4 equivalent oxidation, so we'll have to consider that. So let's go to the paper. And so we're going to start with the 1800 seconds again. Again, 3 sig figs, 3.20 coulombs per 1 second, 96,500 coulombs per 1 mole of electrons. Now here's kind of what's different. We got a 4 equivalent reductions for 4 moles of electrons is 1 mole of O2. And this, since it's STP, we can use our gas law principles. 1 mole of an ideal gas at STP, we said way back in the gas law chapter in first semester, was 22.4 liters. You can go back and watch some of that if you need to prove that to yourself. And so we see coulombs, moles of electrons, moles of O2, and we're left with liters of O2 gas. Again, you're just going to run that through your calculator. We're going to get 0.334 to 3 sig figs liters. Or if you want to go to milliliters, since it's small, you can call it 334 milliliters. Either way would be acceptable since I wasn't specific.